All right, we're going to get going here on the rest of section 12.5. We'll do it 12.5 part 2 here. And so what we're going to start looking at here are planes. And as you remember in the last section, we found that anytime we had two vectors, we could do a cross product of them, assuming they weren't parallel, and get a third vector that was perpendicular to it. All right, it would be normal to those first two vectors. Say this was vector A and vector B. Well, if we think about it, vector A and B have to lie in some plane together. They lie in a plane together, and therefore we can define a plane by looking at any two vectors. Any two vectors we have that are not parallel, we'll define a single plane. And since our two vectors can be cross product together to give us something normal to them, that also gives us a vector that is normal to the plane. And therefore, we really don't even need the original two vectors anymore to define a plane. All we need is a single vector and the idea that that single vector is perpendicular to that plane. And it wouldn't matter if it was the vector that was perpendicular up or a vector that was perpendicular down. Those would both be normal to the same plane. And so it wouldn't matter if you did A cross B or B cross A. Either way, you get a vector that is perpendicular to your single plane that you're looking at. And so you can see here in this picture that's already in here that we have something like this. We have a plane that is being defined there, and we have a vector here that is normal to it, perpendicular to it, just like that. And then in order to define this plane, the only thing we really need to write out an equation for it is we need to know some points that happen to be in that plane. All right? And so let's take a look then at how we can put this to use. So taking a look here, one of the things we have to know is that the normal to our plane here and the dot product of a vector made between 2 points on the plane is going to be 0. No matter what, it has to be 0. So if this is the plane through this point and normal to this vector, then this here must be true. And if we come down here to the bottom, you can see where I took and expanded this n dot p naught p, where p naught is a point in the plane and p is another point. We're just going to leave it in terms of variables x, y, and z. And the given points x naught, y naught, and z naught for p naught, we can write this out. We can expand this. A normal vector, we're going to say, just taken from up here, is ai plus bj plus ck. So that's just some vector that happens to be normal. And then what we have here, to find the vector for p naught p, we have to do p, all the other components of p minus all the components of p naught. So that's going to be x, some variable x, minus a specific point x naught, some variable y minus a specific point y naught, that's our p naught point, and then z minus z naught. So just like that, and then we can take and actually do the dot product, which is this next line here below, where I did a times x minus x naught, and b times y minus y naught, and c times z minus c naught, and it gives me this scalar equation right there. And that right there is the equation for the plane where this is true. And it equals, and of course, equals 0. That's the last part you have to add on at the end. So that takes us to this line right here. And you can see that the coefficients out in front of the parentheses, you can just read them off. They correspond directly to the components of our normal vector. And you see them right there. And then one last thing you can do is the next line where we can expand everything else, multiply the A through the parentheses, the B through the parentheses, and the C through, just expand them through, and then move all the constants to the right-hand side. And we get a constant D that ultimately is AX naught plus BY naught plus CZ naught. But then that leaves us again with just our coefficients being the components of our normal vector, and then D on the other side is some combination of, of this part. Let me get a different color here. Is this, it's this part right here this is what D is, but we can condense it all down because AX naught, BY naught, and CZ naught are all just constant scalar values that we can combine together. Okay? So let's take a look here. We want to find an equation for the plane through P naught 3, 0, 7 is the point. Sorry, that won't go away. Okay. And it's perpendicular to this line here. So again, we're going to go with this vector n dotted with P naught P must equal 0. And so that means that 5i plus 2j minus k, right? This vector here dotted with P naught P. So what we need is to go ahead and write this out in terms of this P naught and then the just general XYZ, another XYZ unknown point on that, a variable point. It can be any other point, assuming we know this one fixed point. So this would be x minus x naught, which is -3, plus y minus 0 plus z minus 7, just like that. And then we can actually go through and do this. So x minus -3 is just going to be x plus 3. This is just going to be a y. This is just going to stay a z minus 7. So we can go ahead and dot product this. So 5 times x plus 3. 2 times y. And then negative k, or not negative k, -1, sorry, it's right there, -1 times z minus 7, just like that. And then this has to then equal 0, okay? And so this right here is actually a plane, but we can go ahead and do this. We can take it and say 5x plus 3 plus 2y minus z minus 7 equals 0, just to get rid of that -1 there. And then the last step, if you wanted to do, you could take one more step and make this, or actually really 2 more steps. This will be 5x plus 15 plus 2y minus z plus 7 equals 0. And then you can move all the constants to one side and have 5x plus 2y minus z equals, and then we'll add our constants together. This is plus 15 plus 7, so that's plus 22, so it's a minus 22 on the other side. All right, and so that's pretty much it for that example right there. I think this would have been a fine answer, but this is also a fine answer. They're both equations of the plane. It doesn't really tell us which form it wants it in. All right, so for the next one, I want to leave this for you to try on your own. This time, instead of giving you a normal and giving you a point, you're given 3 points on the plane. So what you need to do is think about this, 3 points on the plane. I think we did something similar to this before, but you can take this, if this is point A, B, C, I didn't really draw them according to what the coordinates were there, but this, you could have vector AC and vector AB, and you're going to want to take advantage of AC crossed with AB, and that will give you some normal vector to it, right? And so that you'll get some third vector, let's make that red, the normal vector, and then that will be the normal vector to your plane, okay, that B and C lie in, okay, perpendicular to the plane. Let me make that perpendicular to the plane, like that, okay? So give this one a try. Once you get that normal vector, you should be able to go through and do it just like the other way. It doesn't matter which point you pick for P naught of A, B, and C, all 3 will work, but try a couple different ones and see what different forms you get when you use a different point. They should all, see what happens if you choose A as P naught, or then try it again, but use B as P naught and see what the difference is, see what you turn out with the equations. All right, next, lines of intersection. So whenever we have 2 vectors that are not parallel, they're going to intersect at some point in the intersection of 2 planes. All right, here's one plane, here's the other plane coming up through it right there. They're going to intersect in some line, right, where they cross, okay? And so they have to intersect if they're not parallel. How do you tell if they're parallel? Well, they're parallel if and only if, that's what IFF is, remember that. They're parallel if and only if their normals are parallel, right? Because if I look at this one right here and I draw its normal like that, and I draw this other one's normal like this, well, the two planes aren't parallel, they're crossing, and their normals aren't parallel. However, if I have a plane like this, and its normal is like this, and then I have another plane that's parallel to it, well then its normal is also going to be parallel to the other one's normal. They're both parallel to each other. And so you can just simply check the normals to see if two planes are parallel. So here it says, find a vector parallel to the line of intersection of the planes. And so here what we have is two planes intersecting, and we need a vector parallel to them. So if we look back at this picture up here, right? So we have two planes. What we can do is find the two normals, and then if we take a cross product of these two normals, right? Let me get a third color here. If we do the cross product of those two vectors, we're going to get a vector that's perpendicular to those two, and that vector that's perpendicular to our two normals is going to be parallel to the line of intersection, right? It's going to be perpendicular to those two right there, and therefore parallel to the line of intersection, because those two have to both be perpendicular to the line of intersection, because the line of intersection is right along those two. So we need to pick out the two vectors, or two normals. We can pick out two normals by simply reading off the coefficients. If you look, where was that? Back here on this page, this is the form we have right there. We have ax plus by plus zz equals z. That means we can pick out a, b, and c as just our components of a normal vector. So we come back here on this first one. Let's just call it vector a. We'll call it 3i. Actually, I don't even want to write i's. Let's just do, well, I'll do it here. We'll do it different ways, different times. 3i minus 6j minus 2k. And then b vector, you got to get used to writing these in different forms. So I'll do it in the ijk form here. So this will be 2i plus 1j, so just a j. Didn't draw that very well. Just a j. Minus 2k. So that right there is now two vectors that are normal. And then in order to find a line that is, or a vector that is parallel to that line, you simply do the cross product of the two normal vectors. Okay, so you would want to do, you'd want to go ahead and just solve this. And I'm going to leave this for you to do it, but we'll call this vector v, our vector that's parallel to them is just going to be what? I, j, k. And I'll leave you to try and do this 3, negative 6, negative 2, 2, 1, negative 2. So you go ahead and find that, and then that'll give you a vector that is parallel to the line of intersection. Okay, and then here we have a nice picture of it. You can see that this normal to the first plane, this normal to the second plane are both then, if we do that, are perpendicular to the line of intersection. So that drawing's a little better than my little hand sketch, but that's exactly what we were just doing. So now, how in the world do you find the actual line of intersection? Well, here, I'm going to leave this one for you to try. Wait, is that the same 3x minus 6y? Yep, that's the same one. So what we're going to do is copy this over, and we'll go ahead and actually do it and get that one done for you. So we'll bring this over here and we'll say, here we go. This is our vector that has to be normal to them. So what we're going to have is the I component is going to be this minor in here. So that's going to be negative 6 times negative 2 is 12, and then minus negative 2 for the other cross. So it's that way and then that way. And then that's in the I direction, and then in the J direction, we're going to have negative 6, so plus negative 6, so that's 3 times the negative 2, and then minus negative 4, and that's in the J direction, and then plus, and then we'll do in the Z direction is going to be negative 6 times negative 2, it's going to be 3 times 1, 3, and then minus negative 12, and that's in the K direction. So that right there is going to be our vector. So what do we have? We'll have 14i minus 2j and plus 15k. Okay, so that's our vector that is parallel to the intersection. And so then the last thing you have to ask yourself is, well, that's parallel to it. That's fine. We can have this plane here and then this plane over here, and they intersect right here, right? And our parallel vector could be way over here, basically from the origin. So we need to actually figure out how to make it be that vector over there. So the trick here is we essentially have 3 unknowns, right? And so what we're going to want to do with our 3 unknowns, and we only have 2 equations here, right, is we are going to want to pick what we're going to have to just set one of the variables. And so what I would do here is, well, one, I'm going to take this whole thing and move it back to the previous page, right? I'm going to take this, copy it, and let me move it over here just to get it out of our way. And so we'll have it over here already done. Paste. There we go. So you can have it right there. But when I come back over here, I really only need this part. There's not a lot of room here. So, all right, let's get rid of all of this, and I'll put this here. And there we go. So now what I need to do is go ahead and pick one of these. So what I'm going to do is I'm going to set z equal to 0, and then what that does is my equations from above, they get simplified. I'll end up with 3x minus 6y minus 0 equals 15, right? That's this one right here. So I have that 0, so I'm just going to make it equals 15 because I don't have a lot of room. And then this one here, again, the z is going to go to a 0, and I'm going to end up with 2x plus y equals 5. All right, now at this point, I have 2 equations and only 2 unknowns. All right, and I can solve these. And this will give me a point that's on the line. And, at some point, this line, assuming it's not, a very rare situation where it never crosses z equals to 0, this will be a point on our line. And so I would just go through and go ahead and solve this. So, for example, I might take this one and say, all right, y equals 5 minus 2x, and then I can substitute that up into the first one and have 3x minus 6 times 5 minus 2x, right, equals 15. And then I can solve this for x. And if I go through and solve this for x, I'm going to end up with 3x minus 30 plus 12x equals 15. And so this gives me 15x equals 45, right? 15x equals 45, which means x equals 3. And so now all I need to do is go back up here, plug this in right there, right? So I've got one of them. I've got z equals 0, and now I just need the y, and so I have 5 minus 6, that's negative 1, and so I have y equals negative 1 there. There's my third coordinate for my point there. And so the point 3, negative 1, 0 is on the line. And so now I have a vector parallel to, and I have a vector, and I have a point on the line, and you can go through and do what we did before when you had a parallel vector and a vector on the line to find the parametric form of the equation, which is what we did in the last section, right? Which was our, what did we do? R of t, remember, was some point p plus v vector t, right? Like that. And so this is what we did and did it in that last section, so, or the first half of this section. And so you should be able to go through and finish that off now, having that point and a vector, a velocity vector that's parallel to the line. Okay? On the next one, you can see here, I went through and actually already solved this. And this one says, find the point where the line x equals 8/3 plus 2t, y equals negative 2t, and z equals 1 plus t intersects the plane. So we have a line, right? We have a plane, and then we have some line running through it, and it's going to intersect it at some point. And that's the point we want to find. Well, this can be done by simply plugging in the x values in for x, the y values in for y, because what do we want to do? We want to find where both of these are true at the same time, where they equal, all right? In other words, a point that is both on the plane and on the line, that is the point where they intersect. So I plug in all those values, which I did here, 3 times x, 2 times y, 6 times z, and I solved it for a value of t. And so this tells me that when t equals negative 1, my line is going to be, have a specific value, but that value is also a point on the line. And so I take that t equals negative 1 value, I plug it back into my equations for x, y, and z, these ones up here. That was a horrible star. These ones up here. So I plug that in, and I go right through to this point, and I get 2/3 for x, 2 for y, and z equals 0 by plugging in that negative 1. I can come over here and do a quick check. I know that that point is on the line because I just plugged in a value for t and got a point on the line. But if I come back in and plug those three x, y was 2, I plugged it in the middle. If I plug them back into this equation for the plane, I see that it is an actual solution for the plane as well. So the point 2/3 to 0, this point right here, is both on the plane and on the line, and therefore must be the point where they intersect, because a straight line and a plane are only going to intersect in one point, and that's a point where they both have the same solution. All right, I kind of made that pretty messy. Okay, so try your way through that one and make sure you understand it and can work through it. All right, over here, we've got finding the distance from a point to a plane. So the distance is essentially going to be the idea that we've got a plane, we've got a point up here, and what we want is this perpendicular distance, right? That'll be our shortest distance from the point to the plane that's right underneath it, and therefore basically is the length of some vector that is normal to our plane. And what we have to look at here is if P is a point on the plane and the plane has a normal in to it, then the distance from any point S, this will be our point S up here, this point S, okay, this point S, is going to be the length of the vector PS onto that. So we have some point P, here's our point P, and if we draw a vector from point P to point S like that, and then we also have some other vector that is normal to it, and remember we can draw these anywhere we want, so I'm going to draw it I'm going to draw it. No, I don't want that color. I'm going to draw it right here. I just used blue. Orange. Okay. I'm going to draw this as my normal vector. It could be greater than or less than the distance to S. It doesn't really matter. Some normal vector there, right? And now if I take and I can project this vector PS onto the normal vector there, its length, when I do that, so if I take PS and I take this component of PS onto N, right, project it over on there, in other words, shine light from this direction and look at the length of the shadow on PS, or the length of the shadow of PS on that normal vector, right, then that length will be the distance from the point to the line. And so I can do that. Here we have the equation that you're given, but I like it this way. It's PS times a normal vector. That way I'm not using just any vector. I'm taking just a normal vector right here that has that length of 1, and therefore when I do the dot product of them together and when I do the dot product of them, I'm going to get just the components that were parallel, and therefore end up with just the length of PS in the normal direction. Okay, and so let's give we can take another look at this. Here's N. In this one, remember this N vector over N magnitude, that is just the normal vector. I just find that one simpler to remember. Okay. So that's those two equal each other. And so here it says find the distance from S113 to the plane 3x, 2y, 6z. So we can pick out a normal vector quite simply by just picking out these numbers out in front. And so you would get normal vector is 3, and I'm going to write this one, this time I'm just going to write it in component form. So 3, 2, 6, just like that. And you can convert that to a normal vector, right? Or a unit vector by doing that over the magnitude of itself, just like that. And then once you find that, you just have to take the vector PS and do a dot product. So the problem here is you need a point on that plane. Well, how do you get a point on that plane? This isn't the right form right here where we could pick out a point on the plane. In fact, if you remember, we need something more like this. We need something that was of this form. Ax minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Then we can pick out the points x, y, and z right there, x naught, y naught, z naught, and that gives us a point P on the plane. But we don't have it in that form, so we're going to put it into that form. And what I'm going to do is I'm going to make this be 3x plus 2y plus 6z equals, and I'm just going to divide this up. I don't see a nice easy way to do it, so I'm just going to make this 2 plus 2 plus 2. And then I'm going to subtract it over. I'm going to do 3x minus 2 plus 2y minus 2 plus 6z minus 2 equals 0. And so I have minus 2, minus 2, minus 2. That is the total 6 that was on the right-hand side. And then I'm going to group these together, like I'd already done, and just factor out that initial coefficient right there. So this will be 3 times x minus 2/3. This will be 2 times y minus 1. And then this will be 6 times z minus 2/6, which is 1/3 equals 0. And now we have it in the form we need it in, and you can pick out a point on the line right there. 2/3, 1/3. All right, so I want you to go ahead and finish this off. You have a point on the line, use it to make the vector PS, and then take and do its dot product with the unit normal, or whichever way you want to do it, this one or this one. Take the dot product and find the actual distance. Okay? Here's a better picture than what I was trying to draw, and you can see it here. Take a look through this, but it's basically the same picture I drawn, just a little neater, where this is our vector right here, PS, and then if we dot it with our normal vector, which we're taking and turning into a unit normal vector, then we end up with this length right here, right? Which is the distance, the length of that vector is the distance from the point to the plane. Okay? Here, we're just taking note that the angle between the two planes is obtained from the angle between the two normals. And you can see that very clearly here. So if you ever asked, find the angle between two planes, simply find their normal vectors and find the angle between those normal vectors. And that's all this example is here. This video is already getting 30 minutes long here, so I'm going to leave this one for you to try. But just pick out your normal vectors. I'll do it for this one. So if we call that I don't know, we can call it normal 1. We'll call this 3, and again, I'll write it in component form just because it's a little quicker than the IJKs. -2, just like that. There you go. And then pick out the other one. And then you kind of have your option. You can try, remember that N1 cross N2, right? I want you to pick between these, would be N1, N2 sine of the angle between them, or you can do N1 dot N2, the dot product has to, and actually it's the magnitude of this one, and so here the dot product is N1 N2, the magnitude of each of them times the cosine of theta. And so then use either one of those to actually go through and find the angle. Try both ways, see what happens. All right, so that's it for this section. The next section will be 12.6, and we'll just keep on moving on. So thanks a lot for listening.